Chapter 2. The History of Electricity. When we flip on a switch, we get electricity instantly, and our lights turn on almost like magic. Behind this everyday convenience of life is a rich and varied history. It has been a journey of almost 270 years since electricity was discovered by Benjamin Franklin, through to the modern inventions we have today, from electric cars zooming around to phones being charged wirelessly. As with every engineering and scientific discovery, intuition has played a key role. When Franklin carried out his legendary experiment, he had to have a good idea of what he would find. He tied a key to a kite string during a thunderstorm and proved static electricity and lightning were one and the same thing. This happened in 1752. Fast forward to 1831, when Michael Faraday realised an electric current could be produced by passing a magnet through a copper wire. This amazing discovery formed the bedrock of today's electricity and how we generate it, through magnets and coils of copper wires in big power plants. Because of this principle, both the electric motor, where electricity is converted into motion, and the generator, where motion is converted into electricity, were born. This was a good 66 years before J.J. Thomson, a British physicist, identified the electron during his investigations of cathode rays. This is but one example of where engineering discoveries predated the underlying physics explanation of the observed phenomenon. The electron was the first subatomic particle discovered. Through his 1897 discovery, Thomson played a pivotal role in revolutionizing knowledge of atomic structure. Under ordinary conditions, electrons, which he initially called corpuscles, are bound to the positively charged nuclei of atoms by the attraction between opposite electric charges. In a neutral atom, the number of electrons is identical to the number of positive charges, protons, in the nucleus. Any atom, however, may have more or fewer electrons than positive charges, and thus be negatively or positively charged as a whole. These charged atoms are known as ions. Not all electrons are associated with atoms. Some occur in a free state, with ions in the form of matter known as plasma. Electrons are nearly massless. They have a rest mass of 9.1 by 10 to the power of 28 gram, which is only 0.0005 the mass of a proton. This discovery was highly significant in its day because this particle was then understood exclusively as a particle. Even before this, James C. Maxwell, in 1861 and 1862, published an early form of his famous equations. He first used the equations to propose that light is an electromagnetic phenomenon. Electricity can also be thought of as an electromagnetic waveform. The equations are a set of particle differential equations that form the foundation of classical electromagnetism and electric circuits. The equations provide a mathematical model for electric, optical, and radio technologies, and for electric motors. The Chicago World's Fair was held in 1893 to commemorate the arrival of Christopher Columbus in America 400 years before. It was attended by more than 27 million people during the 6 months it was running. Many hugely interesting events took place during the gathering, but from the electricity perspective, there was a sort of closure of the debate as to whether electricity circuits ought to be in alternating current, AC, or direct current, DC. 3 brilliant inventors, Thomas Edison, Nikola Tesla, and George Westinghouse, battled over which electricity system, DC or AC, would become standard. During their bitter dispute, dubbed the War of the Currents, Edison championed the direct current system, in which electrical current flows steadily in one direction, while Tesla and Westinghouse promoted the alternating current system, in which the current's flow constantly alternates. George Westinghouse, a business guy, had bought the AC patents from Tesla in 1888. The good burghers of Chicago decided that the Westinghouse system, using alternating current, would be the one used to power the World's Fair there in 1893. This decision ushered in the AC era of electricity transmission and distribution systems. AC remains the dominant design philosophy underlying the movement of electricity today. Electricity grids, as well as conducting electricity from place to place, have played a vital economic role in society. They do so for a number of reasons. If the transmission system is robust, with a certain amount of redundancy built in, it can withstand the failure of one of its lines. Analysts often refer to this as single contingency security, or N1 security. Such robustness and diversity create a network of power plants and lines that is far more reliable than a system that relies on the output from a single plant or a single line. In the end, an interconnected power system needs fewer power plants to meet customers' electricity demands, because all the power plants can use the transmission system to share the responsibility of meeting customers' demand. Some countries choose an N2 reliability criterion. This is a more reliable system, in which two transmission lines can fail and customers are still supplied with power. Grids allow a number of different technologies to be linked together to meet customer demand more reliably. Here in Ireland and elsewhere in Europe, the suite of generation varies. For instance, we have had oil and coal-fired generation, peat-fired, gas-fired, hydropower, and now wind and some solar. Different methods of generation are uncorrelated one with the other, and are therefore more reliable. What this means is that, for instance, gas arrives by pipeline, whereas coal is delivered by ship, and can be stored in a large coal field for later use. Pipelines and shipping are completely unconnected and have no dependency on one another. In practice, this means that any pipeline can fail, and there are no knock-on effects on the shipping industry. Peat-fired generation is native and is independent of perturbations in world shipping. Hydro is also native, and the supply of water has nothing to do with coal deliveries or peat production. Wind dances to its own independent tune. This mix of generation is inherently more reliable than any single generation source. Transmission grids connect generation to consumption, so as to allow generation to happen in a location best suited to the generating station. A really great instance of this is the location of Money Point Power Station on the Shannon Estuary. Here, a mere 30 metres from the shore, there is a water depth of 30 metres. Any and every bulk coal carrier, no matter how large, can be offloaded here. As a hard and fast rule, in shipping, the larger, the cheaper. Another example of suitable locations for generation would be mine-mouth power stations. It is cheaper to transport electricity than coal or peat, and so the generating station can be located where the fuel is mined or harvested, in the case of peat. Transmission grids compensate for the outages, forced or scheduled, of generating plants. It is a characteristic of all thermal plants that outages happen from time to time. If one were to conduct the following imaginary vision, a city of 1 million people needs an electricity supply of 1,000 megawatts during a period of maximum demand. Obviously, 10 such cities would need 10,000 megawatts, or 10 gigawatts. Without a grid, the only way to guarantee 99.9% of supply of electricity is to hold one power station in reserve for each city. An investment in 20 power stations would be needed. If one built a transmission line linking all the power stations together, it would not be necessary to hold 10 power stations in reserve. Approximately 2 reserve power stations would suffice, because breakdowns occur randomly and probably not all at the same time. So instead of having to invest in 10 power stations, only 2 reserve stations are needed. This represents a big reduction in capital investment, and so leads directly to cheaper electricity. Unavailability for scheduled maintenance outages can be planned for periods of low demand, so that no two are scheduled out together. What is described here is an idealized conjecture. Electricity demand varies according to the weather and time of day, but many other factors also impinge on demand. Notwithstanding this, the need for transmission grids is shown clearly. Reliability can be set at the highest level, while the investment in redundant plant can be greatly reduced. According to DNV, 100 million circuit kilometres of grids were operating globally in 2022. The transmission grid system will grow from 7 million circuit kilometres in 2023 to about 16.5 million circuit kilometres, mainly driven by new renewables coming online. Circa 1.5%, 109,000 circuit kilometres, is high voltage direct current, HVDC. DNV believes this will grow fivefold to 480,000 circuit kilometres over the next 2.5 decades. Subsea DC transmission cables will grow 100-fold in capacity, from 1 terawatt kilometre in 2023 to 100 terawatt kilometres in 2050. Until recently, transmission lines were cheap to build, operate and maintain. This was mainly because overhead power lines could be constructed. In Europe, community objections to overhead power lines over land have reached limits which deter all but the most determined from trying to build them. Even where the developers are successful at getting planning permissions and convincing communities, timescales are punishingly long, again preventing most developers from starting the process. Mass electricity didn't exist before 1900, but since then it has proved to be a universal energy carrier. The most obvious uses include lighting the whole world, doing common or garden space heating, cooling and refrigeration, operating machines and appliances, powering laptops or smartphones, scanning humans internally using MRI machines, powering trains, and now cars. But these uses mask the enormous leap forward that electricity facilitated, such as digitization, internet development, global communications, and social media. If human existence can be characterized by any one invention, electricity has to be a leading candidate for such an accolade. We suggest it can now be used in a critically important role as the main lever of decarbonizing the world in a scenario where deploying the supergrid can maximize the energy efficiency and minimize the cost, space, and use of critical raw materials of this process. One of the big advantages that electricity enjoys over other energy carriers is the fact that it is capable of being used directly. It doesn't need to be burned. It is pure power. It creates the magnetic fields of massive density in the CERN particle accelerator used to examine the smallest building blocks of matter. It can be inverted from AC to DC and vice versa, allowing it to be stored in batteries. These batteries can be powered to put back into the grid from the stored energies in the batteries of cars. When renewable energy is used, burning fuels and the inefficiencies and pollution that burning creates can be avoided. Although electricity is the perfect, if abstract, energy, it still only supplies between 20% and 25% of the world's energy needs. Fossil fuels, gas, coal, and oil, still supply the bulk of global energy requirements for electricity, heat, and transport. Hydrocarbons have to be burned to release the energy. As is well documented, fossil fuel use results in CO2 being put into the atmosphere in increasing quantities, which, in 2021, from energy alone, amounted to 40 billion tonnes of CO2 equivalent, and growing in spite of commitments made by countries under the Paris Agreement. This raises the risk of catastrophic impacts that are irreversible for centuries. In Q1 of 2022, electric cars in Europe outsold diesel for the first time. In 2023, electric vehicles, battery, hybrid, and plug-in electric, accounted for 48% of new car registrations in the EU, 35% were petrol, and 14% diesel. The UK brought forward its ban on new fossil fuel vehicles from 2040 to 2030 to help speed up the rollout of electric vehicles across British roads. In March 2023, the EU passed legislation to ban the sale of new petrol and diesel cars from 2035. California has mandated that sales of fossil-fired vehicles will be banned from 2035. Heating is another major area of energy use that is largely provided for by fossil fuels. This generic area will in the future use electricity either directly in electric fires or indirectly using heat pumps. The heat needed to heat premises is low grade, being in the order of 25 to 50 degrees Celsius. In a majority of locations, it will be possible to use heat pumps. They collect heat from the environment, air, ground, or water, and pump it into the premises using electricity. There is a huge gain in energy terms of between 300 and 500% using high-grade energy contained in electricity when it is used in heat pumps to deliver low-grade energy into premises. Electricity is mysterious. Is it a movement of electrons or an electromagnetic waveform? To me, it seems one can explain direct current as a movement of electrons from a higher voltage to a lower one. However, alternating current seems to be more easily understood as a waveform with electrical and magnetic properties. For the engineering-orientated reader, those waveforms are at an angle of 90 degrees to one another. As US environmentalist Bill McKibben noted in the New York Review, because electricity is so much more efficient than combustion, totally electrifying countries would probably cut their primary energy use about in half. So where does it fit in when doing the emissions maths? The UN Intergovernmental Panel on Climate Change, IPCC, has shown we need to cut emissions in half in the 2020s if we are to have any hope of meeting the targets set in the Paris Agreement, and to keep average global temperature rise to no more than 1.5 degrees Celsius. As McKibben acknowledged, there is one obvious route to reaching that goal. We must immediately figure out how to electrify everything we do, and we must supply that electricity with non-carbon energy. The era of setting things on fire, coal, gas, oil, wood, to produce power must end. Instead, we'll have to rely almost entirely on the large flame that burns 93 million miles away. We contend wind plays a critical and complementary role in that mix. Electrification is to climate change as the vaccine is to COVID-19. Perhaps not a total solution, but an essential one, he noted. Critically, electricity generated from renewable sources produces zero carbon emissions, while rollout of electrified smart devices uses energy more efficiently, thereby optimizing the process. Applying electrification to buildings means using electricity for core functions such as heating, cooling, and cooking, while potentially transforming industrial processes that have traditionally been provided by on-site combustion of gas, heating oil, propane, or other fossil fuels. A Boston University study published in 2022 warned, however, inefficiently building electrification risks prolonging fossil fuel use. Decarbonisation pathways need to incorporate more efficient electric heating technologies and more renewable energy sources to minimise strain on the power grid during increased electricity usage from heating in the peak demand months of winter. Otherwise, harmful fossil fuels will continue to power these seasonal spikes in energy demand. Switching to an electric system that powers heating through renewable energy sources rather than coal, oil, and natural gas is a crucial step towards achieving global net zero climate goals. However, most building decarbonisation models have not accounted for seasonal fluctuations in energy demand for heating or cooling, the Boston University study concludes. This makes it difficult to predict what an eventual switch to cleaner, all-electric heating in buildings could mean for the national power grids, especially during peaks in energy use. Published in Scientific Reports, the study presented novel modelling of multiple building electrification scenarios and found that this seasonal surge in winter energy demand will be difficult to satisfy through current renewable sources if buildings switch to low-efficiency electrified heating. The findings emphasise the need for buildings to install more efficient home heating technologies, such as heat pumps. The climate crisis and interlinked nature crisis, which is undermining the biodiversity that sustains all biological life on Earth, cannot be solved by electrification. Too much damage has been done already. And in the hundreds of years needed to get rid of the CO2 from the atmosphere, the heating impacts will continue to degrade biodiverse life on the planet. But electrifying everything can quickly become the great workhorse of decarbonisation. It can be the main driver in ending the reliance on fossil fuels within a tight time frame that makes carbon neutrality by mid-century realisable, while at the same time helping to solve the energy crisis by ending dependence on oil and gas, especially supplies sourced from unreliable despotic rulers. Because the sun doesn't always shine and the wind doesn't always blow, electricity generation from renewables does not deliver a constant flow of energy. They are variable and intermittent, and so we cannot rely upon them for the steady baseload demand for electricity that exists in each region of a country. That said, the days of unreliable renewables are coming to a fast end. Intermittency, once the Achilles heel, can be addressed. Battery technologies are changing and achieving unprecedented efficiency, a trend that will only accelerate. Grid operators are by their nature conservative because their main task as system operators is to ensure electricity supplies are maintained at any price, in a narrow national context. In contrast, we are at the beginning of a new age with the ability to use the vast amount of grid supply for wind and solar, allied to the fact that they are cheaper than fossil fuels and can get cheaper. The missing element is a supergrid, capable of extending across a continent, that uses technology to minimise losses as bulk power is transmitted at unprecedented speed over vast distances to where demand is most concentrated. The Economist Technology Quarterly in June 2022 summarised succinctly the complexities, what is required and where we are now. Endorsing the electrification project, it acknowledged, is constrained by the history of what came before. It combines informed, perhaps idealistic, technical imagination with the kick-the-tires conservatism of good engineering. It depends on the integration of technologies old and new to control immense flows of power, and it is a work in progress. The electricity mystery deepens when it comes to superconductivity. Superconductivity was discovered by Dutch physicist Heike Kamerlingh-Onnes in 1911 when he measured zero resistivity in a sample of mercury. At 4 degrees Kelvin, minus 269 degrees Celsius, That is at liquid helium temperature. Onnes was one of the world's great authorities on extreme refrigeration, that's temperatures near absolute zero. He found an electrical current would flow for years without stopping once started in mercury. Normally, electricity conduction results in heating losses, which follow the formula I2R, where I is the current and R is the electrical resistance. This formula was thought to be universal until superconductivity was observed. A superconductor has a characteristic critical temperature, below which the resistance drops suddenly to zero. An electrical current through a loop of superconducting wire can persist indefinitely with no power source. Superconductors are also able to maintain a current with no applied voltage whatsoever, a property exploited in superconducting electromagnets, such as those found in MRI machines. It has been demonstrated that currents in superconducting coils can persist without any measurable degradation. Experimental evidence points to a current lifetime of at least 100,000 years. Theoretical estimates for the lifetime of a persistent current can exceed the estimated lifetime of the universe, depending on the wire geometry and the temperature. In practice, currents injected in superconducting coils have persisted since 1995. In February 1987, University of Houston scientist Paul Shu, a physicist who had been spending his life on superconductivity, invented the first superconductor that worked at liquid nitrogen temperature, minus 196 degrees Celsius. Liquid nitrogen is very cheap, costing a third of the price of milk, and can be used in everyday applications. This transformed superconductivity from an esoteric and strange phenomenon to something that could be demonstrated on a tabletop. It is said it is impossible to understand superconductivity without a knowledge of quantum mechanics. Cooper pairs of opposite spin electrons are what conducts the electricity in a superconductor. Science has not been able to precisely describe what exact combinations of materials can lead to superconductivity. Compounds which become superconductors at a critical temperature of minus 200 degrees Celsius are available commercially and have been deployed successfully to conduct electricity in Essen, Germany from 2014 and in Seoul, South Korea from 2019. AMSC's Resilient Electric Grid, REG, has been operating in Chicago since 2021, and the world's longest superconducting cable, the 12-kilometer-long Superlink project, is being developed in Munich. The superconductor is an extremely thin layer of superconducting material. It is unable to support itself and needs other layers of thicker, stronger material on either side of it. Figure 2 shows what this arrangement looks like. The superconducting layer, shown in black, is in the range of 3.5 to 5 microns thick. A micron is 1/1,000,000th of a meter. For comparison, the thickness of human hair varies from 0.017 to 0.18 millimeters, or 17 to 180 microns. The amount of material used in superconductors is tiny compared with the amount used in traditional copper conductors. The weight of the superconducting layer uses a mere 1/30,000th of what is used in a copper conductor. If the weight of all the other layers is considered, the superconducting tape weighs 1/180th of a copper conductor. Looking at the entire cable, 7 times more copper goes into a conventional HVDC copper cable, 22 ton per kilometre, compared to a superconducting cable, 3 ton, for a transmission cable with 2 gigawatt capacity. If one were to double the capacity of a copper cable to 4 gigawatts, it would require an additional cable, because overheating would damage the insulation and the cable. In a superconducting cable, more superconducting tape is simply added to increase the capacity. A 4 gigawatt superconducting transmission cable would maintain its dimensions, and its copper demand would remain 3 ton per kilometre, whereas the copper content of a 4 gigawatt HVDC copper cable would double. All the above-mentioned superconducting projects are based on first-generation superconducting cables. They rely on superconductors as conductive material, and they can transfer up to 10 times more power than conventional copper or aluminium cables at much lower voltage levels, which dramatically reduces system cost. And they require a fraction of the space of conventional power cables. However, a superconducting cable must be cooled to very low temperatures, typically minus 200 degrees Celsius, depending on the material, to maintain its superconducting state. A cryostat, often containing liquid nitrogen, keeps the conductor cool. These first-generation superconducting cables are encased in a corrugated steel cryostat, which limits their ability to maintain a state of superconductivity over long distances. They are commercially available, but limited to specific fields of application in the urban power grid. They are often a targeted solution for transporting large amounts of electricity in cities. Second-generation superconducting cable systems are now being developed, including by Supernode, that extend the range to hundreds of kilometres to enable long-distance terrestrial and subsea bulk electricity transfer. Here, too, the superconductor acts as a conductive material, but the cooling and insulating construction is not made of corrugated steel, but of less costly polymers and a smooth-bore inner cryostat, allowing these superconducting cable systems, operating in a closed cooling system, to reach distances of beyond 50 kilometres between the cooling stations. Combined with scale manufacturing processes, this makes second-generation superconducting cable able to transport large amounts of transmission-level electricity. In his book, How to Avoid Climate Disaster, Bill Gates offers the following tip. Whenever you hear kilowatt, think house. Gigawatt, think city. 100 or more gigawatts, think big country. With gigawatt-scale offshore wind being scaled up all over the world, electrification is about to enter its most enabling era. However, without the supergrid exploiting the stunning advantages from superconductivity, the full potential of this energy revolution will not be fully realised. It will become too costly and require too many raw materials. Chapter Key Points 1. Benjamin Franklin discovered electricity 270 years ago. 2. The first modern city electrification happened in Chicago when alternating current, AC, was chosen as the energy format for the World's Fair there in 1893. 3. Electricity is pure energy and needs no combustion when generated from wind, solar, and hydro, as distinct from deriving it from fossils, which need to be burned. 4. Electricity grids, as well as conducting electricity from place to place, have played a vital economic role in society. 5. High-voltage direct current, HVDC, will grow 5-fold, and subsea DC transmission cables will grow 100-fold by 2050. 6. Because electricity is so much more efficient than combustion, totally electrifying countries would probably cut their primary energy use in half. 7. Superconducting transmission cables can transfer up to 10 times more power than conventional copper or aluminium cables at much lower voltages, and require a fraction of their space and raw material use.